In our video, we'll be looking through the energy lens at a ball dropped from a height of 4.5 meters, and we'll be looking at the transfer of potential energy into kinetic energy as the ball drops from the height and bounces back up.
Drop it.
We'll start by outlining our general energy equations. We have potential energy equal to mgh, and kinetic energy equal to 1/2 mv squared. So we'll start with a height of 4.5 meters. And our mass is equal to 1.1 kilograms. And we have gravitational acceleration acting upon the ball, and that's equal to roughly 10 meters per second squared. So the ball starts at rest at height of 4.5 meters, and we can easily find its potential energy with all our variables here in our equation. Potential energy equals mgh. So we'll do that calculation. So we get a total potential energy value of 49.5 joules. And once we have that, we know our potential energy at the beginning of the drop will equal our kinetic energy at the bottom when the ball hits the ground. So KE initial, just like that. So once we have our potential energy value, we can easily substitute that in for KE right here, and then we can plug in our mass, and we can go ahead and solve for our final velocity. So we get a final velocity value when the ball hits the ground of 9.5 meters per second. Thanks.
This here is the displacement over time graph as the ball fell down and bounced back up with less energy.
Since we know our initial potential energy before the ball was dropped of 49.5 joules, we can use the second height after the first bounce to find our difference between potential energy of heat or energy lost due to heat, or just because the system, energy is always conserved except when heat is lost. So the kinetic energy, after the bounce is going to be less than when before it hit, and potential energy obviously is less because it doesn't bounce up as high. So we will use the height of 2.4 meters was our new height times gravitational potential, or the acceleration times 1.1 kilograms. And with that, our new potential energy our new potential energy now is 26.5 joules. So as you can see, if we subtract the difference, we lost 13 joules. 23, my bad. 23 joules of energy due to heat after the first bounce. So in knowing this, we can tell that the system loses about 50 to about 60% of its kinetic energy after each bounce. So pretty soon it comes to a rest. But because the graph is pretty consistent in its displacement, you can find, just dividing the differences in kinetic or potential energy, that the ball loses about 60% of potential energy after each bounce.